Hello, everybody. This is the last lecture of the fourth section of part one of this course, Band Theory of Solids. In this lecture, I will introduce the concept of wave packets. Wave packets are linear combinations of waves, Bloch waves or plane waves, that are localized in space. I will show you how this localization is possible. And through this localization, electrons in crystals acquire particle-like properties. They behave as particles. They remain waves, but they behave as particles. I will introduce the distinction between the phase velocity and the group velocity of a wave packet. And finally, I will tell you a little bit about the bridge between quantum mechanics, which is mechanics of waves, particles described as waves, and classical mechanics where waves are not part of the game. Particles are particles. This bridge was built in the year 1927, 100 years ago, by Paul Ehrenfest, an Austrian physicist. It is known as Ehrenfest theorem. So based on Schrödinger's equation, he derived he was able to show that particles, in some sense, can be described as classical particles using Newton's second law. I will not prove Ehrenfest theorem, I will just state Ehrenfest theorem. But in Ehrenfest theorem and this Newton's second law, the mass appears, a mass parameter, mass times acceleration is the force. So I will introduce the concept of effective mass of charged carriers, electrons, and holes in semiconductors. Let us begin with the concept of Bloch wave functions. Bloch wave functions are modulated plane waves. Here we have this plane wave. The modulation function, which is denoted here as u sub n, and it depends on the coordinate r. This modulation function have the periodicity of the crystal lattice. That is, if you change the argument r by any lattice translation vector, the modulation function will not change. Two quantum numbers are present in Bloch wave function. One is the wave vector k, and the other one is the band index n. Now, the probability to find an electron near a particular point in space is modulus squared of the wave function, and this probability density is has the periodicity of the crystal lattice. Other than this periodic modulation of the probability density, Bloch wave is delocalized. That is, the probability to find an electron, let's say, in a particular unit cell of the crystal is the same for all unit cells. In that sense, electron is delocalized. Yet, in some phenomena, so typically collision events, electrons, despite the wave functions being delocalized, electrons behave as particles. This happens when electrons collide with impurities, with defects, with quanta of lattice vibrations, phonons. And the question is, how does this delocalized wave function shown in the first line of this slide, how does it suddenly get localized? So the answer to that question is that Bloch wave function is derived for an ideally periodic crystal. We do not take into account any defects, any impurities, any deviations from periodicity, not even deviations due to the vibrations of the crystal lattice, due to the thermal motion of the ions that form the crystal. But if those deviations from perfect periodicity are taken into account, block wave functions do not describe electron states anymore. Electron states become more complicated. In fact, they stop being stationary. But, well, because the crystal vibrates, so if the crystal vibrates, then the Hamiltonian, the Hamiltonian operator of the system becomes time dependent. And each electron finds itself in a time-dependent potential. So that's how stationarity is lost. But the good news is that when the deviations from perfect periodicity is not too big, then you still can describe the electron states approximately as linear combinations of the solutions of the time-independent Schrödinger's equation, block wave functions, combined together. So you need to form linear combinations of these block wave functions. And these linear combinations are called wave packets. So let us look at the wave packets in some detail. Let us begin with the simpler situation when you have an electron that moves in one direction only, let's say x direction, and there is no periodic potential. So the electron wave function is a plane wave. And now let us form a linear combination of these plane waves in the form of an integral. So you add up, you multiply a plane wave, e to the power px minus et divided by h bar. Now remember that p divided by h bar is the wave number k, and energy divided by h bar is the angular frequency omega. So this is the plane wave. Each plane wave is multiplied by some sort of an envelope function a that depends on the momentum p. So this function a of p tells you how much a plane wave with a particular momentum value p contributes to the total wave packet. And we will be interested in the situations when these envelope functions a of p are localized in momentum space. That is, they have a maximum at some momentum value p naught, and they have finite width, and they go to zero as you go to the left or to the right from that central momentum p naught. Now, of course, the wave packets must be normalized to 1, so the total probability density must integrate to 1. I still impose periodic boundary conditions, but okay, so probably the integration limits should be from 0 to L, not from negative L to L, like that. Magic. All right. Now, I would like to, okay, so the first question is, are the plane wave states really legitimate states? Are they possible? Not the plane wave, the wave packet states, are they legitimate states? Are they possible? Each plane wave obviously obeys both the time-dependent and time-independent Schrödinger's equation, because if you take the second derivative of a plane wave with respect to space, d2 psi by dx squared, so this is the plane wave integrated with respect to space twice, multiplied with negative reduced Planck's constant squared over 2m, you will get momentum squared over 2m. So take the derivative of this. You will get momentum squared over 2m, which is the kinetic energy. But you can get the same result if you differentiate the plane wave with respect to time and multiply the result by this derivative, time derivative, with I h bar. So both time-dependent and time-independent Schrödinger's equation are respected by each plane wave, as we have known for a long time. As for the wave packet, it does not respect time-independent Schrödinger's equation. Because if you differentiate the wave packet wave function with respect to space twice, the integrand gets multiplied by momentum squared over 2m after canceling out the h bar squared. So the integrand gets multiplied by p squared over 2m, but p squared over 2m is the kinetic energy that corresponds to a given momentum value, and it is not a global energy of the wave packet. So each value of the integrand is multiplied by its own kinetic energy. So the integral is not proportional to the wave packet wave function. Hence, the time-independent Schrödinger's equation does not hold. Is it a bad thing? Not necessarily. It does not mean that the wave packet is impossible in nature. It only means that the wave packet is not a stationary state of the system. As long as the time-dependent Schrödinger's equation, which is more fundamental than the time-independent version, as long as the time-dependent Schrödinger's equation is fulfilled, the wave packet is a legitimate possible state of the particle. Does the time-dependent Schrödinger's equation hold true for a wave packet? And the answer is yes, because if you take the time derivative of the wave packet wave function, multiply the result with IH bar, you will get the same as the negative second space derivative of the wave function in the wave packet state, multiplied with the negative, multiplied with h bar squared over 2m. So this is the kinetic energy, this is the kinetic energy, this integral and this integral are one and the same thing in view of this identity. So, and since the time-dependent Schrödinger's equation is fulfilled, for the wave packets are possible in nature, even though they are not stationary states of an electron. Now, let's investigate these non-stationary states, these wave packets. And in general, this can be a little bit complicated, but let us not complicate our lives. That let us focus on the simplest possible envelope function we can think of, namely a box function. So our envelope function a of p has a constant value, let's call it a naught, in an interval between the central momentum p naught minus delta p to the central momentum p naught plus delta p. Okay, and it is zero outside of that interval. So in a sense, the wave packet wave function is localized in the momentum space. And of course, the advantage of this choice of the envelope function is that we can now perform this integration easily. So our integral, we have to, in the integral, we have to integrate an exponential function, and the integration limits are p naught minus delta p to p naught plus delta p. There is still a small complication here because, so in the exponential, we have two terms, momentum times coordinate and energy times time, and energy is p squared divided by 2m. It is the second order polynomial that we need to integrate. And while it is possible to perform such an integration, the result will involve the so-called error function, but let us simplify our task further and assume that the width of the envelope function a of p is such that the energy does not deviate very much from the linear behavior near in that interval delta p, where the envelope function a of p is different from 0. So then we can approximate the energy function E of p as a linear function. We choose the parameters of that linear approximation based on two considerations. First, the value of energy at the central momentum must be correctly reproduced. So indeed, if you set P to P naught in this formula, the second term becomes 0 and you have E of P naught equals E of P naught. Good, we have correctly reproduced the energy at the central momentum. And second, we wish the first derivative of energy with respect to momentum to be correctly reproduced by this linear approximation when P is set to P naught. And indeed, if you differentiate both sides with respect to P and set P to P naught, you will get E prime of P naught equals E prime of P naught. So we have fulfilled both of these requirements. We have correctly reproduced the value of energy at the central momentum. We have correctly reproduced the first derivative of energy with respect to momentum at the central momentum P naught. Such an approximation is fairly common in physics. You can systematically improve the quality of that approximation by imposing further requirements, such as let us also reproduce correctly the second derivative of energy with respect to momentum at the point P naught. Then this will give you a further term 1/2 E double prime of P naught times P minus P naught squared. Then you can go further and require for the third derivative to be correctly reproduced, and that will give you 1/6 E triple prime of P naught times P minus P naught cubed, plus and so forth. But we will keep, and this is called Taylor approximation of a function. This general procedure is called Taylor approximation. But we will just keep the linear approximation, which is sufficient to, which enables us to evaluate that integral, this integral from here for the wave packet wave function. Now we also define, for brevity's sake, we define the first derivative of energy with respect to momentum at the central momentum P naught. It has the dimensions of the dimension of velocity, right? So let us call it the group velocity, and for now it is just a name. We are not ascribing any particular physical significance to the group velocity. We just notice that the derivative of energy with respect to momentum is measured in the units of velocity. So let's call it the group velocity. All right, so now we plug in this linear approximation of energy right here into the wave packet wave function. And now the exponential depends on the first power of momentum. And we can perform integration. Integration gives, integration of an integral of an exponential is an exponential multiplied by whatever multiplies the argument. Divided by whatever multiplies the argument of the integration variable in the exponential. Then we will notice that in the integral we have something like exponential to the power I delta p x minus v group t over h bar minus exponential to the power negative I delta p x minus v group t over h bar. Then we will recall Euler's identity that exponential to the power I theta minus exponential to the power negative I theta divided by 2I is sine theta. So that's how sine of this delta p x minus v group t over h bar comes up. All right, so this is the final result. This is what we get after the integration. This result has an interesting structure. First, we recognize this exponential to the power p naught x minus e of p naught t divided by h bar. What is this? This is a plane wave. This is a plane wave with momentum p naught and angular frequency e of p naught divided by h bar. This plane wave is modulated in space. This plane wave is finds itself inside an envelope function, which is proportional to sine delta p x minus v group t over h bar, divided by x minus v group t. So the plane wave turns out to be in an envelope. All right, now, it may seem suspicious that what happens when x approaches v group t, then the denominator approaches 0. So you have something divided by 0. So it might seem that the result goes to infinity. No, it does not go to infinity, because in the numerator, you get sine of delta p over h bar times the same thing, x minus v group t. So the numerator also goes to 0 when you are taking the limit of 0 over 0, and you have a ratio of two functions, each of which goes to 0. When x approaches a particular value, then you need to apply the L'Hopital rule, and that L'Hopital rule, in this particular case, will give you a finite number, which is, so this ratio when x approaches v group t, this ratio approaches delta p over h bar by L'Hopital rule. All right, so now what about the probability density? How does the probability density look? The probability density associated with the plane wave is the modulo square of a plane wave, I should say, not the probability density, but modulo squared of a plane wave exponential to the power I times something, some real number, is 1. The modulo square of exponential to the power I times any real number is 1. So the probability density is proportional to the modulus squared of this envelope function, but that envelope function is real valued, so envelope function squared. And here is the plot of this envelope function squared, so sine squared of delta p x minus v group t over h bar divided by delta p squared x minus v group t squared divided by h bar squared. When x approaches v group t, this ratio approaches 1. This ratio quickly goes to 0. As it goes to 0, as you move to the left or to the right of this peak, it has a peak at x equals v group t, and the argument of sine becomes 0. The probability density becomes maximized. The probability density decreases quickly as you move to the left or to the right from that maximum. It can perform a few extra oscillations, but in general, it quickly goes to 0. As time goes by, the peak of this probability density gets shifted. It moves with the velocity v group t, because again, the probability density is maximized when the argument of sine squared goes to 0. So this maximum of the probability density moves with the group velocity, which is, let me remind you, which is the first derivative of energy with respect to momentum at the central momentum p naught. And moreover, by considering this wave packet, we have obtained also an interesting and important result known as Heisenberg uncertainty principle, derived by Werner Heisenberg in 1920s, one of the founding fathers of quantum mechanics. So notice that the probability density in the position space x depends on the position. The position is multiplied with delta p. Delta p is the width of the envelope function in the momentum space. And the position in the numerator is multiplied with delta p divided by h bar. And in the denominator, it is x is multiplied with delta p and divided by h bar. And everything is squared. So if you ask yourself, what is the width of this wave packet in the position space, then you need to set this function f to some value So this is an estimate. It doesn't need to be like here. For some reason, I chose the value to be 0.3, but to some reasonable value, maybe 1/2. The width of this wave packet in the position space, let us call it delta x, or twice delta x, because in the expression for the wave packet, x is multiplied with delta p divided by h bar, set in the condition that f of x is given by a certain number, let's say 1/2 or whatever number you choose, but reasonable, you get an equation for delta x, for x, and the solution will be some number. It will be V group T plus some number multiply with h bar divided by delta p. So this number times h bar divided by delta p will give you the width of the wave packet. In other words, the product of the wave packet width in the position space delta x multiplied with the width of the wave packet in the momentum space delta p will be of the order of h bar, of reduced Planck's constant. And this is Heisenberg's uncertainty principle. The better you localize your wave packet in the momentum space, that is, the smaller the width delta p, the more delocalized your wave packet will be in the position space, the bigger the width delta x will be, and vice versa. The better you localize the wave packet in the position space, the smaller delta x, the larger the delocalization in the momentum space, that is, the larger delta p. All this discussion has been performed under an explicit assumption that the energy includes only the first order term in momentum. But what if you include the second order term into the energy momentum relation? Because after all, kinetic energy is momentum squared divided by 2m. Well, if you include the second order term and you perform a similar calculation, then it will turn out that the wave packet is not stationary. It is not stationary, it moves. The peak of the wave packet moves in the position space, but also the wave packet will get broader in time. It will increase in time. Electrons in crystal constantly interact with deviations of the crystal lattice from perfect periodicity. And so you can think of it as of this dynamics of electrons in a crystal as follows. So let's say initially an electron is in the wave packet state. As this electron moves, it's the peak of that wave packet, the position of that wave packet moves with the group velocity. At the same time, the width of the wave packet gets bigger and bigger, and then at some point of time, an electron described as a wave packet collides with maybe an impurity, maybe a defect of the crystal lattice, and this results in a reduction of the wave packet width. So the wave packet width is also non-stationary, and the collision events control the width of the wave packet. So the collisions actually, they keep the width of the wave packet on average that is fixed. Electron wave packets never become delocalized. They never cover the whole crystal. The wave packet width remains finite. All right, so all right, now let's talk about the phase and the group velocity of a wave packet. We still are dealing with plane waves. We form the wave packet with plane waves, and the phase velocity of a plane wave is the velocity with which the wave front moves in space. The wave front is defined by the locations of all points where the phase of the plane wave has a given fixed value. So kr minus omega t is fixed. And from this condition, that the phase is constant, k dot r minus omega t is constant, it follows that the position of the that the wave front moves with the phase velocity, which is given by the ratio, the magnitude of the modulus of the phase velocity is given by the ratio of the angular frequency to the wave vector, modulus of the wave vector. Now, the phase velocity is a vector, so the direction of the phase velocity is the same as the direction of the wave vector. Whereas a wave packet moves with the group velocity, and in three-dimensional space, the group velocity is a given component of the group velocity is the ratio of energy to a given component of the momentum. So, but you can form a vector using these three components of the group velocity, dE by dpx, dE by dpy, dE by dpz, or alternatively d omega by dkx, d omega by dky, d omega by dkz, where omega is the angular frequency and k is the wave vector. So, so this is the generalization of the group velocity for a wave in 3 dimensions, because in the previous slide we have discussed the one-dimensional wave. All right. Now, of course, you can construct a wave packet not from plane waves, but for electrons in crystal, you can use Bloch waves to construct the wave packet, but the general expression for the group velocity will remain the same. So, of course, your Bloch waves must belong to the same band, let's say to the conduction band. The general expression for the group velocity as a vector formed by the derivatives of the energy in this band, in a particular band, with respect to momentum, remains valid. So now let us still restrict our attention to a one-dimensional, hypothetical one-dimensional crystal, in which case the energy, and let's assume that you have a conduction band in this crystal and a valence band, and let's focus on the conduction band. As you know, the electrons which get promoted from the valence band to the conduction band, they typically end up near the bottom of the conduction band, and so their wave packets can be constructed using the states of closely spaced momenta near the bottom of the conduction band. Near the bottom of the conduction band, the energy can be expressed as a second derivative of momentum, like that. So EC is the energy at the bottom of the conduction band. So the idea is to use Taylor expansion, second order Taylor expansion, as I have described already when we expanded energy with respect to momentum. In this second order Taylor expansion, we aim at correct reproduction of the energy at the conduction band minimum, and the parameters must be chosen so as to correctly reproduce the first derivative of energy with respect to momentum near the conduction band minimum, and the second derivative of energy with respect to momentum near the conduction band minimum. So this is what we do. So EC is the energy at the conduction band minimum. If P is set to PC, PC is the momentum at which the conduction band energy has a minimum. When P is set to PC, you get the second term equals 0, and you get E of PC equals EC. Okay, check. The first derivative of this approximation with respect to momentum is d2E by dp squared at P equals PC times P minus PC. And when P is set to the momentum PC, at the conduction band minimum, then P minus Pc goes to 0. So the first derivative at the minimum is 0. Okay, so we have correctly reproduced the first derivative. And finally, the second derivative of the energy momentum relation, that is the curvature of this curve, is indeed d2e by dp squared at p equals pc. So the second derivative of this is this, which is also correct. Now, notice that the second derivative of energy with respect to momentum has the dimension of inverse mass. So instead of d2e by dp squared at p equals pc, we can write 1 over m electron star. M electron star is the so-called electron effective mass. Okay, so this is the electron effective mass. What is the role of the electron effective mass? This role has been revealed. It can be revealed using the Ehrenfest theorem, which I have mentioned in the introductory slide of this lecture. Ehrenfest theorem tells us that if you have a wave packet and the wave packet is subjected to an external force, so there is an external force acting on an electron. This force may be due to an external electric field or magnetic field or a combination of both. Then the central momentum, P naught, of the wave packet will no longer be fixed. It will change in time, and its rate of change will be exactly the force that acts on the electron. What happens to the group velocity of the electron? The group velocity is the derivative of the energy momentum relation with respect to momentum, evaluated at the central momentum P naught. The rate of change of the group velocity can be found using the chain rule. So you d by dt dE by dP at the value P equals P naught, where P naught is now time dependent. According to Ehrenfest theorem, dP naught by dt, the rate of change of the central momentum P naught, is the force F. So using the chain rule, you can differentiate. You want to find the time derivative of this dE by dP of the group velocity. You can differentiate the group velocity with respect to the central momentum, which is the second derivative of energy with respect to momentum squared, and then multiply the result with the rate of change of the central momentum P naught, so dP naught by dt. And if your force now, okay, so the second derivative of energy with respect to momentum is inverse effective mass of the electron, and dP naught by dt is the force. So if the force is due to an external electric field, then the force is negative elementary charge, electron charge, negative elementary charge, times the electric field, which will be denoted in this course as cursive letter E, capital E. And of course, I will be using the cursive E for the electric field in order to avoid confusion with the energy. All right, so acceleration turns out to be equal, given by the ratio of the force to the electron effective mass. And that's the role of the electron effective mass. It is the parameter which enters Newton's second law. Now, same treatment can be applied to holes, but now holes live near the top of the valence band. And the hole is a state which is not occupied by an electron. A hole lives near the top of the valence band. Near the top of the valence band, we can approximate the energy momentum relation with the second degree polynomial. The parameters of that polynomial are chosen so as to correctly reproduce the value of the energy at the top of the valence band. Let's call it EV, and the momentum at which the valence band has the maximum is called PV. So if you set P to PV, you will get E of PV equals EV, and the second term is 0. The first derivative of the energy momentum relation is 0, so there is no first order term. in the right-hand side, and the second derivative of energy with respect to momentum is also correctly reproduced. It is negative. The second derivative is negative because this parabola, energy momentum curve, is a parabola, and it is convex down, right? So looks like that. So the second derivative is negative. So the inverse of the second derivative is the whole effective mass. And since the second derivative of the energy momentum curve near the top of the valence band is negative, I wish to have the effective mass positive, I put a minus sign here, okay? So whole effective mass is a positive number. It is expressed as a positive number. All right, so the typical values of the electron and hole effective masses are of the order of from something like 1% to something of the order of 1 electron mass, free electron mass. If the band is flat, the flatter the band, the higher the effective mass. There are also the so-called heavy fermion systems where the bands are so flat that the electron effective masses reach the values of the order of a few hundred free electron mass, or even up to 1,000 free electron mass. All right. So in this discussion, we have analyzed hypothetical one-dimensional crystals. Now, of course, the real crystals are three-dimensional objects, and as a result, the electron and hole effective masses are really not numbers. They are matrices. They are 3x3 matrices whose entries are related to the second derivatives of energy with respect to various components of the momentum, x, y, and z. When it comes to the discussion of conductivity, it turns out that the entries of those 3x3 matrices can be combined into scalars. There is a unique procedure that tells you how to do that. So as a result, you will get a scalar, and that scalar is the actual effective mass, which can be found in the literature, in the textbooks. Now, let us finally, in this final slide, let us discuss the role of the hole effective mass and also the charge of the holes. Why do holes, which are absence of electrons in the valence band in particular states, why do they behave as positively charged particles? So let us form a wave packet out of electron states in the valence band, with the central momentum P0 close to the valence band edge. And we apply a force due to an electric field to electrons. So this force acts on the electrons in the valence band. The charge of an electron is negative elementary charge, minus E, times the electric field, capital E. We ask ourselves, how does the group velocity of this wave packet, electron wave packet, not hole, but electron wave packet, how does the group velocity change in time due to this force? Again, we apply Ehrenfest theorem. The rate of change of the central momentum is the force minus E, small e, times big E, minus elementary charge times the electric field. What happens to the group velocity? We apply the same reasoning as before. The rate of change of the group velocity can be related to the rate of change of the central momentum using chain rule. So it is the derivative of the group velocity with respect to momentum at the central momentum P0. That is, it is the second derivative of energy with respect to momentum, second derivative at the central momentum P0, times the rate of change of the central momentum. Okay, maybe it should be dp0 by dt. And on the previous slide, On the previous slide, I have it right, dp naught by dt. So there you go, dp naught by dt. Now, the second derivative of energy with respect to momentum is negative inverse effective mass of a hole. Okay? It is a negative number, and the effective mass of a hole is a positive number, hence this minus sign. And dp naught by dt is the force on an electron, so negative elementary charge, the charge of an electron, times the electric field. This minus times this minus gives me a plus. So the group velocity of this wave packet is given by the product of elementary charge, the charge of a positive particle, times the electric field divided by the whole effective mass. So the wave packets, due to the negative curvature of the energy momentum relation in the valence band, the wave packets formed by Bloch states near the top of the valence band behave as positively charged particles with the whole effective mass, and those positively charged particles are interpreted as holes. So with that, I would like to thank you all for your kind attention, and in the next lecture we will begin our discussion of semiconductors as such. Thank you. Bye.